Hello, this is Mr. Huff, and let's talk about program design and pseudocode. So, when you're thinking about a program, there are three levels of behaviors. Complex behaviors are things like the robot walks up to a door, recognizes the door, decides which way to turn the doorknob, and turns the doorknob while pushing the door open and then passing through the door. So that is a lot for a robot to do. There was a robotics competition last year, and most of the robots failed when they got to the door. One of them, it was pretty fun because it grabbed a hold of the door and turned itself over, so it couldn't even complete the task because it knocked itself over while trying to work a doorknob. So this is complex behavior. Simple behaviors are like where you take a simple single task and you break it down into little parts, but it's just like one thing, like turning the doorknob would be a simple task. And then basic behavior, these are the single line commands that tell a robot what to do. For example, like in this example, it says start a motor. So complex behaviors are composed of lots of simple behaviors, and simple behaviors are composed of lots of basic behaviors. That is the high level view of program design. So when you are talking about pseudocode, what I'm saying is you're just going to think about how your program is structured without paying attention to syntax, what the specific commands say, what the values should be. You're just describing each line of code in an English phrase. So, and I like the examples here, turn a motor on for 3 seconds, follow a line until it runs into a wall. So you're you're describing what that little piece of code is going to do, and we have some more examples in just a moment. And this talks about breaking down your simple behaviors into basic statements and your complex behaviors down into simple behaviors. So you want to start from your most complicated thing, drive it all the way down to the basics of what's happening. Okay, so for more examples of pseudocode, it might look like this. Warning light turns on before the fan starts for 3 seconds. I would suggest that you break that up into multiple statements. Turn it on, and then start fan, and wait for 3 seconds. So that's more like what we'll see in here. Okay, let's get down to this a little more. So here's an example of a simple program using pseudocode. So we start with program starts, and then you turn on an LED for 3 seconds, you turn on a motor until a button is pressed, and then after you do that, another light turns on for 3 seconds, and then you end the program. One of the things that's really important, and this is the third big idea I have for you in this, is it is crucial that you understand your inputs and outputs on your microcontroller before you start programming. So this is something you need to define ahead of time. Where are your inputs? Where are your outputs? Because if you don't know that, it's going to be very difficult to make your program work. So always start with that first. And another thing, we'll be using the PLTW template. This is where the pseudocode is going to be placed in. So I expect you to write your pseudocode before you do any code. And this is a better example. So you can see right here, the first part, lines 5 through 27, well actually through 29. This is kind of a header statement in the PLTW template where you would put in what the title is, who the people are working on it, the date you worked on it, section, I don't care so much about, put activity in there. And then it's going to describe what the program does, and then it has the pseudocode here, just kind of outlined. That's nice. And then you just copy and paste that down into your task main in between these brackets and turn it into single line comments. Okay, so this is the structure that we're going to be using for our program design, is this part right here where you have lots of single line comments. Okay. And it's also important to make sure before you start programming that you check your labels and you make sure you're use the debugger to make sure everything is working properly. It's really frustrating to get into a program and you think you're receiving input from something, and then you figure out about halfway through that, hey, that's plugged into the wrong socket and not even seeing anything, so you spend a long time debugging something that was very simple to fix. All right, yeah, this is just, let's pause. Let's say we have a program, this is a really complicated one, it's going to turn on the motor for 5 seconds. Okay, so the top part up here, it's the configuration of your microcontroller. That's the first thing it has to do. And then task main is like think of it like begin program. So this is where your main program lives, and the programming we'll do is going to be just using task main for most of it. We may define, we'll probably do some functions, but this is the main program. So this is where the main program starts. Anything that happens between these two brackets is where your program lives. And you can see the commands here. Start the motor, and it picks a motor. This is the name of the motor, and then it gives it a value. Let's talk about these values. It has 63. So the value for a motor can vary between negative 127 and positive 127. So that will tell it to turn counterclockwise and then clockwise, and then in the middle at 0, it's not turning at all. Okay. It is important to note that there are a few numbers, the numbers that are close to 0 on either side. Let's say you wanted to go really slow, so you put in a 6 and instead of 63, and it may or may not work. These motors have what is referred to as a deadband, and what's happening there is it is telling the motor to do something. It sends a small amount of current, but it's not enough to get the motor started running. And so that's important to be aware of. There is a point where the motor will stop working. And here's another frustrating thing is it's different for every motor. So some are easier to turn, so they work under lower current conditions, and some are harder to turn. Another thing that makes it frustrating is as your battery gets, starts running down, let's say it's down to half a charge, that deadband can get bigger. So when you're using low speeds, you might want to keep in mind that it might be a good idea in your robot design to use a gear system to slow the motor down, so you're turning at a higher rate on your motor and getting a slower speed through using a gear system. Okay, so start motor. So we told the right motor to turn on at 63. If you think about it like a percent, it's not far off. So that's about half speed. Then you're going to wait for 5 seconds. So this literally makes the program wait for 5 seconds. Pretty complicated, right? But what it's doing in that 5 seconds is that motor is turning the whole time. And you have to keep this in mind. If you start a motor, you also have to tell it to stop. So the stop motor command is what tells that to shut down. So this is just going to drive forward for 5 seconds and then stop. And then at that point, there's nothing else in the program. So if you run this program, it's going to go bzzz for 5 seconds and then stop. Pretty straightforward. We've already talked about program design, and this is just another way to think about it. You have some basic behaviors that go together to form a complex behavior. So when you're troubleshooting, it's best to troubleshoot each individual basic behavior to find where the problem is, rather than trying to troubleshoot the complicated behavior. And some ways to do this: you can use comments to test things and to block things out. We've talked about temporarily turning off parts of your code, so there's an example of that. It also has some features in the integrated development environment where you can highlight a section and comment the whole thing out by toggling it. I almost said thingle. That's weird. All right. We have lots of sample programs to go look at so that you can work from models. Most of my career, I usually started with a model of something that was close to what I wanted to do and then adapted that. So I guess that's hacking, right? For our projects, we're going to be using PLTW natural language. And what they have done is for the robotics portion, they have taken things like inline trackers, which would take lots and lots of basic commands to make happen properly, and they've taken a bunch of commonly used basic commands and turned those into simple behaviors that are identified with a single command like inline track for time. So recognize that when you use these natural language commands, it's actually pulling in a lot of basic behaviors and combining them all, so you don't have to do all that part. It's all kind of like simple behaviors described as basic commands. That's what the natural language does for us. Otherwise, you'd be doing a lot of extra coding just trying to make a sensor work. At this point, I would encourage you in ROBOTC to go through and look at the text functions browser. It'll be on the left side, and start exploring the file structure under natural language and sensors and timing and that sort of thing. See if you can start understanding what's inside each one. What does arcade control do? What's forward do? What's stop do? So those are the things I want you to go ahead and start reading. I can go through and explain each one, but I think you can go through and explore and it will be more meaningful. So look at robot motion, look at movement. We need to talk about motor reversal. So let's say you design a robot that has 2 motors on it. It has a left motor and a right motor. And if you tell both motors to go forward, then one is going to be spinning the opposite direction of the other one because they're pointing opposite directions. And your robot is going to go in a circle when you tell it to go forward, and when you tell it to turn, it's going to go in a straight line. So that's really confusing. So what you can do is, in the motor and sensor setup, you can choose one of the motors to always run reverse of what the other one does. And what that does for you is now they both turn the same direction when you tell it to go forward, and when you turn, it turns properly. So that's why you need to be aware of motor reversal. You also need to go look at the special commands and look at the until statements, the kind of things you can. This is like controlling program flow. Do this until this happens is what you're doing. And then wait is something we'll use a lot. And this, keep in mind that it's normally in, yeah, it says in seconds. And then you can also use thousands of seconds. We're going to use probably just wait time. Another thing to keep in mind is as your battery drains, your motor behavior changes. They will get slower when the battery is partially depleted. And if you're using timers to control movement, your robot is not going to move consistently. So explore what the different, so the last thing here is like touch sensors it talks about. These are basically just buttons, and the little cautionary statement is about something that's called key bounce. When you press a button, there's a little time when you're pressing and when you're releasing where it sends a lot of different values. So what we do is we build in a little tiny wait command before we check it again, and that way when you push it, it's gonna have one response, not 100. So, and seriously, sometimes you'll get like 30 or 40 like alternations between 0 and 1 as it's being contacted and being released. So you need to always put this little bitty wait statement in here after you have a button push, or your robot will do some unexpected things. And that's all.